Well, thank you, the organizers, for inviting me. I'm going to talk actually about the supercurrent in the integer quantum Hall effect, and some of you have seen this much of the data which I'm going to present about half a year ago in San Sebastian, but I'm going to also try to present some new results. The work was done primarily by my former student, Chun-Tin Ke, and the former postdoc, Francois May. The introductory material here is again something many of you have seen. Is going to be an introduction of the ballistic Josephson junctions in graphene and measurement of superconductivity, first at zero magnetic field and then in the quantum Hall regime. And finally, I'll try to talk about the possible origins of the observed supercurrent. As an introduction, it's convenient to talk about the hybrid Josephson junctions made out of superconducting contacts to topological insulators or quantum spin Hall systems, which have helical modes on the edges, and the reef-bound state can be made by taking an electron, say, from the bottom contact to the top, and reflecting the Hall of an opposite spin in the opposite direction. So each edge here can carry a supercurrent, and two edges together result in a magnetic field interference pattern which is similar to a squid. Now, for the quantum Hall, we have Cartilage states where both electrons and holes move in the same direction. So we cannot take an electron and reflect it as a Hall within the same edge. Instead, we have to think of a counterpropagating Hall on the opposite edge of the sample. And the idea that such current-carrying Andreev-bound states could exist was expressed early in the 90s by Ma and Zuzin, who have this circular sample with quantum point contacts, and they speculated that there could be current where an electron goes clockwise in one edge, and the Hall is retro-reflected, continuing moving counterclockwise in the other half of this circular sample. So we are going to discuss whether that's indeed the mode of transport or there are alternative explanations at the very end of the talk. But right now, let me start by introducing our samples. They are made from those exfoliated graphene sandwiched in boron nitride coating. Very clean ballistic sample. And contacts, edge contacts made by etching the thumb edge of. You hear me well this way? I think that noise, the voice is kind of breaking. Okay, let me try to adjust it. Tell me if it doesn't sound right. Okay, so. The contacts are contacting graphene from the edge. They are made from molybdenum rhenium alloy, which is type 2 superconductor with a critical temperature of 10 Kelvin, and it can withstand several Tesla. We are measuring the resistance of the sample in a 4-probe geometry where we only have two contacts, but we are passing current and measuring voltage separately. Here's the conductance measured as a function of gate voltage on 4 samples on the same chip. We have normalized the conductance by the width of the sample, which is listed here. So only one junction was of a different width than the rest of them. And you see that conductance is very close for all 4 samples, which tells us that since conductance does not depend on length, the junctions are ballistic. And the contact transparency is consistent between different junctions. It is very high on the N side, approaching ballistic limit, which is the dashed line here. On the P side, there are semi-transparent PN junctions, which reduce the conductance somewhat, but again, those PN junctions are very similar between different samples. Now, the partial reflection from the p-n junction results in those oscillations of conductance which is visible for the shortest samples. And the same oscillations are also visible in the critical current, which is shown here. The map is resistance versus bias and gate voltage. The dark region close to zero bias is a supercurrent. It is larger on the N side, small on the P side. And there are oscillations visible here in the normal resistance and also in the magnitude of the supercurrent. Those are summarized here. The critical current oscillates in phase with conductance. Now, we can also extract from the same measurement by making vertical cuts the value of the superconducting delta from the multiple Andreev reflections. We find delta of about 1.2 millielectron volts. And finally, we can go and look at the physics of these ballistic junctions by comparing the short and long junction regimes. In the short junction regime, you have this familiar cosine phase dependence of the energy of the Andreev bound states, while in the long junction regime, the states should be equidistant, separated by the essentially energy spacing corresponding to the round trip of an electron and holes through the junction, and they have linear current phase relation. It was predicted very early on in, I guess, the first paper of Kulik on the subject that the critical current in the long junction should depend exponentially on the temperature as a result of summing over those multiple levels. It should be e to the minus kt divided by delta E, where delta E is proportional to the level spacing. We have here a set of samples of different lengths, starting from 200 nanometers to 2 microns, which have span this whole range from a short junction to a long junction. The characteristic length over which the transition happens is a coherence length made out of the Fermi velocity in the metal and the superconducting delta in graphene, which is about 500 nanometers. So for 200 nanometer samples, we have this steeper than exponential decay of the critical current, and we can fit it with the formulas for the short junction regime. While for the longer junction, and actually also for an intermediate junction, we see that there is a clear exponential decay of the current with a slope which is the same for different gate voltages, as expected for graphene, which has V-Fermi, which is independent on density. And finally, the slope here scales correctly, meaning the shorter the sample, the larger delta E here. I'm going to skip this for the sake of time, but we have measured this parameter as a function of length. And we have also measured the prefactor. So although the temperature dependence is known, the prefactor in the long junction regime is not known. The value of the critical current is zero temperature as compared to, say, ICRN or compared to the number of modes. And we clearly see that there is some universal behavior at large gate voltage where the ratio of the critical current to the number of modes to the delta E extracted from the exponential slope saturates at a constant level. The critical current is a switching current here, and the estimates that I can make indicate that the junction should be overdamped. I believe the hysteresis between switching and retrapping is caused by heating. If you have underdamped junction, you would expect a much more rough edge here because there would be significant histogram of switching as you change the gate voltage by a little bit. This smooth behavior the smooth behavior of the critical current as a function of gate voltage is typical for the overdamped junction. We have studied that not in this very sample, but in other samples by providing dissipation through the resistors in the leads, and the behavior was the same. And there we could trace the hysteresis between the switching and retrapping being caused by heating. So essentially, you can check that the difference between the switching and retrapping could be provided by heating elsewhere on the same graphene chip and to find that heating provided by this retrapping current is responsible for the suppression of the critical current. So I don't think that the fact that the temperature dependence is correct, I don't think it's a coincidence, so I believe that we are measuring the true critical current and not just a switching current. And I would be interested to discuss the possible reasons why this is not working, although I agree that it appears highly suspicious. Let me move on let me move on to the magnetic field measurements. So this is a measurement of the Fraunhofer pattern where we are measuring the uniformity of the current distribution across the widths of the leads, two different samples which we are later studying. Now again, this is not a pure Fraunhofer pattern. You can find deviations, and we have studied them separately, but I don't have time to talk about this now. I'll be happy to talk about that after the talk. So this is finally the data in the quantum Hall regime, where we have the magnetic field as the vertical axis and gate voltage on the horizontal. At high fields, you see this Venn diagram of quantum Hall plateaus, which below this parabolic line switches to the supercurrent regime where resistance is greatly suppressed. This regime has been studied before in various graphene samples. This transition to the supercurrent has been identified and at least interpreted first in this work by Geim's group, who pointed that below this parabolic level, the size of the cyclotron orbits is larger than the size of the sample, so you cannot have yet quantum Hall, but instead you can have current carrying Andreev bound states which bounce a few times from the contacts, but also from the edge of the sample, thereby completing the trajectory. Now, we are going to be interested in this regime where typical measurement shows finite resistance. But we are measuring it now at low excitation current. It turns out that on the left panel here, I was measuring it with finite bias current, which was suppressing any superconducting features with scale smaller than a few nanoamps. But if you're measuring it on the sub-nanoamp level, there are suddenly many spots of suppressed resistance, which are, as I'll show in a couple of view graphs, correspond to the supercurrent. Now, you can see those two sets of data in a slightly different way if you alternate lines measured at a constant field at finite bias and zero bias, which is what I'm showing here. Again, that's the same data, but now you have alternating line, each second line having suppressed resistance compared to the lines measured at high bias. Another way to look at this data is to make cross sections. So we actually make this cross section as a function of bias and constant field, and then you measure maps like this. So this is a map of supercurrent across several plateaus. These are two cross sections at zero bias and finite bias, which represent the behavior when the supercurrent is present or suppressed by high current. And finally, just staying at one point in gate voltage and magnetic field, you can see this supercurrent and corresponding behavior in the differential resistance. Now, much of what we are interested in is the behavior of the supercurrent as a function of magnetic field. So here I'm showing two interference maps measured as a function of bias to reveal the supercurrent and small variations of magnetic field around a large quantizing field of about 1 Tesla. So here, these two are measured on nu equals 2 and minus 2 plateaus, and we see that the current oscillates with the same periodicity in the two maps, and this is roughly the same periodicity as at zero field. So that suggests that the current is flowing along the edges of the sample, resulting in something like a squid behavior, or, as we'll discuss later, perhaps not quite a squid. Now, Another measurement is shown here, several filling factors ranging from 2 to 6 to 10, again, the same periodicity in magnetic field. Now, just to show you the overall evolution, because we are moving over a wide range of magnetic field, as you are exiting this Fraunhofer behavior at small field, the interference becomes completely disordered, if you wish, completely random. That is the regime of the Andreev bound states which are bouncing off the walls of the sample. And then when you cross that parabolic contour and transition from the semi-classical regime to the quantum Hall regime, only then the pattern becomes periodic. So I'm arguing that this pattern is not a natural continuation of the Fraunhofer pattern. So the periodicity here must be explained by different reason than the supercurrent in the zero field regime. Yes. No, because your current is not flowing in nice one-dimensional channel. So it is expected to be suppressed if it goes around. So the big question, which I'm kind of for later, but of course you know about it, is whether the current is somehow flowing on some spurious channels along the edges, individually, sort of like in that topological picture, topological spin Hall effect, or is it flowing around the complete sample? It is quite suppressed compared to the, I had the estimate, no, I don't have the estimate here, but it 10 nanoamp, so that scale for the current flowing along one edge with fixed transmission, and it should be greatly suppressed if the current is flowing around the circumference of the whole sample. It's the same for the low and high field, and that's where we are getting to. It's a periodicity corresponding to 2E and not 1E predicted in this mechanism. So let me, for the sake of the public who have not seen this talk, yes? Well, you see, the problem with this one is that it could be that disordered not only because of the nature of those trajectories, but also because of the fluxes you are trapping in the lead. So we even did not try to compare it to minus 15 millitesla. So, because the flux spinning will be different, yeah. This is so robust, and again, probably if you go to minus the same field, it will shift in phase, but the periodicity is quite robust as a function of gate voltage or changing the magnetic field. Any more questions? There seem to be a question. Not physical map, no, but a map is a function of gate voltage and magnetic field. Yeah, I'll show that's in the next view graph. So the question is, if you have the electrons and holes moving in a certain direction along a certain edge, and for the Andreev bound state, you need to take a hole in the opposite direction compared to the incoming electron, and hence you have to couple electrons and holes on the opposite sides. How do you do it in a large sample with large superconducting contacts where the electrons and holes are separated by a large distance? It was suggested in this paper that the electron and hole modes are coupled by the hybrid electron-hole mode propagating along the edge of the superconductor, which can quasi-classically quantitatively explained by taking an electron, letting it complete half of the cyclotron orbit, bounce off the superconductor as a whole, bounce again, convert to an electron, in this way mix electrons and holes into this neutral mode. So the suggestion of this paper was that these modes are coupling in as an electron approaches a superconducting contact. It couples to one of those modes, and then on the other end of the contact, you have some amplitude of coupling to the hole, which then propagates, again, has some amplitude to couple to this mode and convert to an electron on the other end. Now, here are the evidences that we have for this type of behavior. I'm showing here the resistance of the sample, resistance as a proxy of measuring supercurrent, since I cannot easily measure or present a full three-dimensional map as a function of gate, field, and bias. I'm taking two cuts at 0 bias and at finite bias, 0 nanoamps and 3 nanoamps, to show the map of resistance in the state where the supercurrent is suppressed. That is not a normal state yet, because the junctions, the leads of the junction are still superconducting, but the supercurrent in the junction is suppressed. And 0 bias, where you are sitting right at the middle of that nonlinear IV curve, and resistance is suppressed due to the supercurrent. So here you see that as a function of magnetic field at constant gate voltage, you'll have the same periodicity that I've been showing before in the maps of magnetic interference. And you see that the phase of oscillations is changing with the gate voltage. So it's not just a simple squid behavior, but you have some dependence on the gate voltage. And this behavior is consistent with this picture where the edges are sensitive to the gate voltage. They are changing their size as the gate voltage is applied. In fact, if you work through the argument in the paper Binneker and Quarters, there is this very suggestive phase factor, which looks like the flux through the area of the junction minus the distance of this hybrid mode from the superconducting contact. So that's the area of this trajectory, which is going around the circumference. And through the dependence of that distance on gate voltage, you get the coupling between magnetic field and the gate voltage. So gate voltage changes D, and hence changes the flux flowing through the bound state. Now, that is an argument in favor of the mechanism which I'm proposing here. Now, the question is, well, what do we have against this scenario? Whether we can distinguish the scenario which I was describing so far, which is consistent in terms of the behavior on the gate voltage, of the phase on the gate voltage, but perhaps you can argue that here there will be also somehow dependence on the gate voltage. So what if there is some region of the sample where the holes or electrons can counterpropagate against edge state? So for example, it is known that electrostatically there will be a density buildup near the edges of the sample, or perhaps you have some dangling bonds. So that is the new material compared to what I was showing some of you have seen, and that's what I want to discuss now. So let me first summarize what do we have for possible questions to the first mechanism which I've been describing so far. It works fine if you are looking at this dependence of the phase on gate voltage. That's in fact how we have originally thought it is explained. And the problem with it is that the prediction is H over E, so single electron kind of interference, while we measure H over 2E, which is a 2-electron periodicity. And one of the explanations which is found is a charge poisoning. But I believe that this does not really work here, meaning adding or removing an electron from this trajectory does not flip the sign of supercurrent as it was doing in the quantum spin Hall system. So alternatively, I would want to think about the Coulomb interaction, which was neglected in the original theory paper. Essentially, spin up and spin down electrons were added to this trajectory at the same gate voltage, which I believe in this case, given that we have edges where 2 electrons would be floating as electrons, if I'm considering spin up and spin down electron in the 2 opposite spin states. And then 2 holes in the 2 corresponding states would also be floating in the same physical region. And if I estimate the Coulomb energy corresponding to interaction of those edges and those edges, given that they carry about 1/10 of electron charge and the rest of it is smeared along the superconducting contact, the Coulomb energy turns out to be quite large, which can split the Andreev states corresponding to spin up and spin down, and in principle could lead to doubling of periodicity. Now, in the second scenario, of course, the periodicity is naturally expected to be given by 2 electrons, so there is no problem. So we need some ways to distinguish the 2 scenarios, and here what I have again is the second scenario, that where you have some spurious channels along the edges. Yes? So the current is quite small. It's decaying in a certain way, and we have measured it, but it's not exponential. So the first measurement was done in a ballistic sample in the normal regime, right? So it was a huge current which you can trace over a large range of temperature. Here you're talking about a small current with whose temperature, yes? It's rather power law than exponential. I'm not making any statement of the value of this current, because when you're dealing with an apparent critical current whose apparent Josephson energy is smaller than temperature, clearly it's not a true critical current. And hence its dependence on temperature can be something complicated. This is a critical, 1 nanoamp is 20 millikelvin, right? This is sub-nanoamp. So this is some remnants of the supercurrent rounded by thermal fluctuation. It should, right? But I'm just saying. It should be larger than temperature. It should be of the order of tens of microvolt, so 100 millikelvin. Yeah, I'm assuming that is the same, which can be suppressed if the modes are softer, because H bar omega is replaced by delta, which then will give you smaller energies. So I'm talking about more qualitative ways to distinguish it, because again, I have the temperature dependence here, and it is more, it is a power law. It's not exponential, this one. Okay, so, but we did try to distinguish the possible mechanisms by looking at the dependence of the critical current on the geometrical sizes of the sample. And in fact, the very first samples we have measured, which were made on the same measure, it happened that one of them was narrower and longer, and another one was wider and shorter, and this one clearly had more supercurrent. So it looked like the length of the edge is less important than the length of the region along the contact. So essentially this sample was barely showing any supercurrent at all, which to us was telling that if the currents were flowing separately along the edges, it would not care that the edges are separated by a long distance, and the shorter lengths of the edges here compared to the sample on the left would result in a larger supercurrent. Again, the result was that this current had the sample more supercurrent. The second argument against the scenario 2, that was the scenario 2 of two independent supercurrents along the edges, is that if you want to build the density buildup, which certainly happens in those samples, it would occur at the transition between different quantum Hall plateaus, while we observe the supercurrent throughout the plateaus. So it is unlikely that it is some channel which happens just at the right magnetic field when there's just the right filling of at a certain density, and you get a channel counter-propagating compared to the proper direction. And finally, those samples at higher temperature, in fact, have nicer quantization than they show here. If you look at the values of the plateaus, they are greatly distorted compared to the quantized value. But you should remember that here we are comparing the data measured at different bias. So we are applying a bias of some norms, which drops some microvolts at the sample, tens of microvolts, but still those small energy scales than the superconducting critical temperature. So the leads stay superconducting, and they modify the resistance of the sample even though there is no critical current. On the other hand, if you take the same samples and increase temperature, even at temperature of the order of 3 Kelvin, you have fairly well-formed plateaus. So if you want to have a counter-propagating state, you can still say, well, you know, this plateau is not perfectly quantized, but the degree to which it is not perfectly quantized is shown here. So it's something. Some 10 nanometers. Probably something like 10 nanometers, something of the order of magnetic lengths. Separation. Yes. Oh yeah. So So if this is those are 100 nanometers or 2 microns, and the edges are some tens of nanometers away from the edge. Yeah, so it's mostly going close to the geometrical edge of the sample, and we are talking about small variations of, say, area compared to the geometrical area of the sample. Okay. Now, another argument which kind of brings it close to your question a second ago is that the direction in which those fringes develop in the function of magnetic field and gate voltage. So here we are comparing the P side and N side, and we expected that if the change of the phase of those oscillations is due to the sample sort of swelling as you increase the gate voltage, making it more, adding more electrons or more holes, we would have these fringes with an opposite side on the p-dope side and the n-dope side. Essentially, you would be making the samples, the area of filled with electrons and holes, larger when you increase the gate voltage either in positive direction or in the negative direction. And correspondingly, the fringes would be anti-parallel, will have opposite slope for the p side and the n side. Instead, we find the same slope on the p side and n side. These maps are oriented in the same direction, so there is more negative voltage on the top, and magnetic field grows to the right, so you see that there is a slope, positive slope on both maps. And in fact, it is much smaller for the electrons. And that, I believe, is a result of having the p-n junctions. So for the n doping, for the electrons, the edge state is running very close to the metal, while on the p side, there is also a p-n junction. So there is a larger distance between the metal and the edge state, and there is also larger sensitivity on the gate voltage. Finally, do we have time? Yeah, so that's kind of the last test that we did here. We did samples with different geometries. So primarily, this was a geometry we studied. We have the regularly shaped sample and the leg-shaped sample, which has an extension of one of the edges. And we have thought that this would allow us to immediately compare the two scenarios. So in the scenario where, the first scenario where the current goes the whole circumference of the sample, there will be no current in this leg-shaped sample because the distance here will be too long. On the other hand, if you have scenario number 2, namely the current is flowing separately on both edges, we will have supercurrent on the short edge of the L-shaped sample, and that would allow us to distinguish the two scenarios. So when we measure the sample, we have, that's an L-shaped sample, we have found, comparing the zero bias and finance bias map, that there is clearly some suppression, very small one, suppression of resistance for the L-shaped sample, which would indicate scenario 2, current flowing along one edge. The only problem was that it is still periodic, and it is periodic, the periodicity given by the area of the junction itself, not the extension region outside. After which we realized that, in fact, those two regions are differently doped. The region between the contact and the extension are doped in slightly different way. Based on the position of the neutrality point, we can say that graphene is p-doped while the contacts are n-doping. So for the n-doping of this region, we have higher doping between the contacts. So we have more modes. Potentially we have some modes which are reflected from this leg. And then we have still this contour going around the sample, while for the p-doping, we would expect that there will be more modes going inside the leg. And indeed, when we measured this sample in the p-doped regime, we have found that there are no signs of superconductivity. I'm not showing for comparison the high bias map, but it looks essentially like this one. And for comparison, this regular sample in the same range of filling factor and in the same scale of the color map had clear signs of superconductivity, so this periodic suppression of resistance at zero bias. So overall, we are still leaning towards the first explanation, the regional explanation with electrons going around the circumference. If so, there should be those hybrid electron-hole modes, neutral modes running at the edge between the superconductor and the quantum hole. And the question of periodicity, the doubling of the 2E as opposed to predicted 1E is still remaining open. Thank you.